In this series of videos, we're going to look at the integral test and how we can estimate sums, and this starts what I consider to be the meat of the chapter. We're going to see several tests, of which the integral test is one, for determining whether a series is convergent or divergent. Let's dive in and write down what the integral test is. Suppose that f is a continuous, positive, decreasing function on the interval from 1 to infinity, and we're going to let a sub n equal f of n. I'll note right now f is continuous, but a sub n is not, because a sub n is going to be terms of a series. With that as background, then the series, which is the sum as n goes from 1 to infinity of a sub n, is convergent if and only if, that's IFF, which symbolically looks like a two-headed arrow. So the series is convergent if and only if the integral from 1 to infinity of f of x dx is convergent. Now to unpack that if and only if, that is to say, part 1. If the integral from 1 to infinity of f of x dx is convergent, then the sum as the sum as n goes from 1 to infinity of a sub n is convergent. Part 2 says that if the integral from 1 to infinity of f of x dx is divergent, then the sum as n goes from 1 to infinity of a sub n is divergent. I need to make a couple of notes. The first one is that the index and the interval don't have to start at 1. And when I say the interval, I mean the lower limit of the integral. The second is that f doesn't have to be always decreasing. It just has to eventually. See, what we're talking about is, I'm going to erase this, but what we're talking about is a function that's positive and decreasing. And we're saying that if the integral is convergent, then the series is convergent. Let's talk about the integral. If the integral is convergent, and we'll just say this is starting at 1, then the area under this curve is finite. Well, if we compare that with a function that, let's say, starts out increasing, but then eventually goes decreasing, then it doesn't matter where I start the integral, the area under this curve is finite, the point here being that a finite amount at the beginning of, well, near the origin, won't affect the convergence of the entire thing, right? So it just has to be decreasing eventually, and the interval and integral in the index can start at numbers other than 1. What this means for us is that if I have a series and I'm trying to test whether it's convergent or not, if I can integrate it from, we'll say for now 1, from 1 to infinity, then the answer to that integral will help me know what's going on with the series. For instance, the integral from 1 to infinity of 1 over x to the p dx converges if p is greater than 1 and diverges if p is less than or equal to 1. Thus, the sum as n goes from 1 to infinity of 1 over n to the p also converges if p is greater than 1 and diverges if p is less than or equal to 1. I'm going to put that in a box because we're going to refer to it quite a bit. That series, the sum as n goes from 1 to infinity of 1 over n to the p, is known as the p series. So it follows that the sum as n goes from 1 to infinity of 1 over n, which is 1 plus a half plus a third plus a fourth, and so on, diverges. Because in this case, p is equal to 1. More to the point, really, p is less than or equal to 1. This is true even though the limit as n approaches infinity of 1 over n is equal to 0. Now, you may recall that for a series to converge, the limit has to be 0. But I also said when I told you that just because the limit is 0 doesn't automatically mean convergence. Sometimes people write that on tests. And I'm like, why would we have gone through the whole rest of the chapter if all we had to do is say the limit is 0? Finding out that the limit is 0 is basically step 1. So in general, we want to look at the limit as n approaches infinity of a sub n. If it doesn't equal 0, then stop. You're done. The series is divergent. If it does equal 0, then you start running tests. And that's what a good chunk of this chapter is about, is learning what the tests are and how to apply them, and also when to apply them. We'll save the proof of this one for later in this series of videos.